All right, and related rates, what the heck are they? Well, if you've been in calculus and you've been in class, you've probably already seen them a little bit in class and have been a little bit confused, or maybe a lot confused. This is sort of like the hardest topic in derivatives because it's word problems. Everyone hates word problems, and everyone hates differentiation with weird stuff. So you kind of mix those two together, and these get pretty rough. The reason I put this incredible block of letters here is to point out and just drill home the thing I'm going to keep drilling, which is that whenever you're doing a related rates problem, all the derivatives have a dt downstairs. dt, 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 dt. You notice these are just all these letters are ones I made up. dA dt could mean the rate of change of area. dr dt could be the rate of change of radius. P could be pressure, V could be volume, J could be javelin throws, Q could be quantity, N could be number of things. But because they have T downstairs, that means the units are going to be in time. So you notice that, like, if we talk about how fast someone's driving, it's meters per second, right? There's time downstairs. If I asked you, how much do you pay in rent? Well, it's dollars per month. So a unit of time is always in the denominator whenever you're talking about rates. And that's why every derivative we're going to take is going to have a t downstairs. This is derivative of y with respect to t. And the units, therefore, are going to be, if y is in meters, t is in seconds, this will be meters per second. dl dt could be the rate of change of the length of something. Could be in centimeters, if the word problem is in centimeters, could be meters, whatever. But dl dt is the rate of change of L with respect to t. So hopefully this didn't blow you away too much, but I just want to drill that in. So whenever we take the derivative of an expression, now we're going to be doing it in terms of t, not x. So traditionally, if you had f of x equals x squared in any previous chapter or even previous section in calculus, the derivative would have been f prime is just 2x, right? The reason there was no d weirdness was because it was all in terms of x. But then in the previous section, we got into implicit differentiation. So we had to take the derivative of something like, x plus y. And then we'd have the derivative of x was still 1, but the derivative of y was all of a sudden dy dx. So it turned out that if you take the derivative of anything besides x, you're going to have to put a d something dx next to it. And that's what's going to happen here. Even though there's never going to be a time, like the letter t is never going to appear in the formulas that we use in related rates. We're going to use things like the equation of volume. The volume formula for a sphere is 4/3 pi r cubed. The area of a circle is pi r squared. The Pythagorean theorem, again, there's no time in there. It's just a bunch of distances, right? Side length, side length, side length. These are all in meters. And yet for this section only, for related rates problems, we're always going to take derivatives of these things in terms of t, which is kind of wacky, but what that means is that all those letters I showed you on the previous page, you're going to have to write down next to these things, just like it was implicit differentiation again. So if we take the derivative with respect to t of this entire equation, we'll just do it one term at a time. Derivative of volume, or v, with respect to t, is just dv dt. It's just like in the implicit differentiation, when we took the derivative of y, got a dy dx. So dv dt is going to equal 4/3 pi, that's just a constant. So now the only variable on the right side is r cubed, right? What's the derivative of a power? Well, it'd be the old power, which is 3, times r squared. But then, just like implicit differentiation, I need that dr dt next to it. So the deal is that whenever you're taking the derivative of these things in related rates problems, whenever you take the derivative of any variable whatsoever for any reason with any rule, you're going to have a d whatever dt next to it. Derivative of v is just dv dt. Derivative of r cubed is 3r squared dr dt. There's that d letter dt after everything we do. So now let's do this one. Derivative of area is just dA dt. And then derivative of r squared, just like last time, is going to be 2r dr dt. All right, Pythagorean theorem is another formula we're going to see a lot, especially in the upcoming video about triangles. Because triangles just happen a lot. So Pythagorean you'll see all the time, but you're going to be taking the derivative of it with respect to t. So in this particular case, we're talking about x, y, and c. I guess there are three sides of a triangle. So we'll do the power rule on each one of these. We'll get 2x. But then we have to have that dx dt is sort of like the price we pay for taking a derivative of something other than t. And then the 2y, the y squared, same thing happens, 2y dy dt. And same thing happens to c. Oops, equals 2c dc dt. All right, so we're going to get lots more practice with this. I just want to use this first part of this video to drill in that whenever you take the derivative of anything in the related rates chapter, it's always with respect to t. I mean, I've seen like 2 problems in my entire tutoring career that were not with respect to time, and they were sort of more basic problems, not these harder ones. So here's the formulas. Where do we get these formulas? Like, how do we know what formula to write down to begin with to take a derivative? Well, it turns out that we need to get really good at spotting the words in the problem that would give you a derivative. So for example, right now we're just going to practice naming variables. So if you saw this sentence or this little piece of a sentence in a related rates problem, let's just write down the letter we'd want to write down. So they're saying find the rate of change of volume. So how fast is volume changing? Well, if you followed what I was talking about before, that would be dv dt, would be the rate of change of volume. And that's what they asked for. Find the rate of change of volume. So that's d volume dt. And rate just kind of automatically means time, like I said. All right, so let's say they want to know how fast is the area of the circle changing. So what's the name of the variable that they're asking for? Well, they're asking for the rate of change of area. So if we call area A, which makes a lot of sense, then they're asking for dA dt. So that's the rate of change of area with respect to time, or the rate with which area is changing. So sometimes they're asking for that, like all the sentences I've given you here, they're asking for a variable, but they also could have said, hey, find the rate of change of area when the radius is changing at 3 centimeters per second or something. So then you're like, oh, rate of change of radius. Well, gee, that's dr dt. How fast is the water level changing? Well, I don't know. We'd have to give the name of that, we'd have to give the water level a name, like, I don't know, d for depth. So then we're looking at dd dt, which looks silly, but of course, you know, this part's always the same, so just whatever letter you put here must be the variable in the problem. Let's do some more. How fast is the rabbit's weight changing? Well, W seems like a good letter for weight, so let's just see how fast that's changing with respect to time. How fast is the plane's altitude changing? I don't know. Let's call it, you know, we already used capital A for altitude. We could use A again, or we could just use P or something, like maybe P for plane's altitude. I don't know. So that'd be dP dt. Doesn't matter what letter you pick, because what's going to happen is on these problems you always have a diagram, and any quantities you use, you'll end up labeling on the diagram. So if you decide to call the altitude P, you're going to have a drawing at some point, you know, maybe it'll look better than mine, of you know, P as being the plane's altitude. Not a problem, you just got to know which letters you're using and what they correspond to. How fast is the circumference of a circle, C, growing? I don't know. That's sounds like a rate of change to me. So you can see how no matter what they ask for or what they give us, we're just going to pick a letter that represents that thing and then put a D in front of it and put it over a dt, and that's the rate of change. What is the rate of change of price? I don't know what this problem's about, but I know the rate of change of price is probably going to be dP dt. Now the reason we're doing this is so we'll be able to plug in, because when we take the derivative of some formula during the course of solving that problem, there's going to be a price in the formula. We take the derivative, we're going to end up with a dP dt, so we got to know either what to plug in or what to solve for. We'll see how that works in a minute. Right now we're just getting practice turning words into derivatives. A gas tank is being filled at 5 gallons per minute. All right, so what we're looking at now is the part of the problem where, you know, the previous 2 slides we looked at if they're asking for something, what's the name of that thing? Now we're talking about given information. So if a problem began that a gas tank is being filled at 5 gallons per minute, what they're saying is that's the rate of change of volume of gas, because the gas is coming into the tank. So I mean the rate of change of volume of the gasoline in the tank is 5. And we could put, you know, gallons per minute units on it just to keep track of stuff, whatever. A human hair grows at 0.5 centimeters per day. Well, that's the rate of change of the length of the hair, right? So dl dt is equals 0.5 centimeters per day. An elevator is going up at 3 centimeters per second, or 3 meters per second. So what do I call that? I don't know. Maybe the height of the elevator is just h. So the rate the elevator is going up is dh dt, and they're saying that's 3 meters per second. Now don't worry, we'll get lots more practice with this. I just want to sort of drill in the point here is with everything is a derivative with respect to t. The radius of a balloon is increasing at 2 centimeters per second. dr dt, right? Because the rate of change of the radius, and they're saying that's at 2 centimeters per second. Now this is just information we'd end up plugging into the problem, and we'll see how that works in the next video. All right, so there you go. Hopefully we drilled it in. Everything's derivative with respect to t, and you've got to get good at sort of going through the problem and figuring out, you know, if they give you some information, what variable name do you give to that? Because a lot of stuff they're going to tell you isn't just a radius or a length or a weight. It's the rate of change of the radius or the weight or the length. So that's why the given information is not just going to be volume equals something, it's going to be rate of change of volume equals something. But don't worry, we'll get lots more practice with this. And you might want to remember this video is here, because what's going to happen is you're going to start doing these problems, and it'll make it look not necessarily easy, but like doable. And then you'll get some problems, then you'll start, everything's easy until you actually start doing it. So come back and watch this video, get re-drilled one more time about the d over dt thing, and get back to it.